problems 19 through 24. So we're going to start off. This is the section on 4.5 and on 5.1. That's the ones we're going to be covering. And this first one says find the vertical, horizontal, and oblique, which you can only have, you can have a vertical asymptote, but remember you can only have either horizontal or oblique. If there are any of the rational function, write none if something does not exist. So when you're looking for your vertical asymptotes, you want to factor the denominator completely. So this would be 2x over x, and that would be, looks like factors of 6 that add to -5 would be a -2 and a -3, but they multiply to +6. You'll also want to factor your numerator as well if it's got anything you can factor, because sometimes things in the denominator are not vertical asymptotes. They are removable discontinuities or holes. So when we look at this, notice there are two factors in the denominator and they do not cancel out. So that means we have two different vertical asymptotes. So anything in the denominator that doesn't cancel out is a vertical asymptote. So then we set them equal to 0 and solve it to get the equation. So one of my vertical asymptotes is x equals 2. The other one would be set equal to 0 and move it over, so x equals 3. So remember, those are vertical lines. To figure out if you have a horizontal asymptote or an oblique, you want to check the degree of the leading coefficient on top over the leading coefficient on the bottom. So the rule goes that it's essentially long division. If the power on top is smaller, you cannot divide into this, so that means you have a horizontal asymptote of 0. Think about it goes in it 0 times. If your degrees match, you have a horizontal asymptote, and it is the leading coefficients, because you would say that because the degrees match, you just have to get the coefficients as a ratio. So that would be, if this was squared, that would be 2 over 1. If the top is a higher power than the bottom, it's not a horizontal asymptote, it's an oblique, and you need to do long division to find the equation. So this is the case 1, where we know that the top power is smaller than the bottom. So if you asked how many times does x squared go into 2x, the answer is 0, so it's y equals 0. That means that we have none for obliques, since you cannot have oblique and horizontal at the same time. So that is for that first one. Let's look at number 20. It says find the vertical, horizontal, and oblique asymptotes, if any, of the function below. So again, we're going to factor this. So I'm going to pull out an x squared and a 3. That would leave me with x minus 2. I'm going to factor the bottom. This is an x minus 2 and an x plus 1. Notice this time there is a cancellation of a factor. So this actually is reduced down to 3x squared over x plus 1. Okay, so let's talk about what we know. The vertical asymptote is only the factor that is still in the bottom after we've reduced. So x plus 1 equals 0 or x equals -1. Let's check whether or not this is horizontal or oblique. You can do that in one of two ways. I recommend using the reduced function because it's easier to do long division on, because this one is going to be an oblique because the top power is higher than the leading power on the bottom. So there's going to be no horizontal asymptotes, because that only happens if you have either you can't divide or the powers match. So the oblique is found by doing long division. So we're going to put x plus 1 into 3x squared, and I always put placeholders, plus 0x plus 0. So x goes into 3x squared 3x times, multiply that by everything out front, and then when we do long division we have to remember to change the signs. So then this is -3x plus 0, and then we'd say x goes into -3x -3 times, multiply that by everything out front. And it doesn't even matter after this point because we don't use the remainder here. The oblique asymptote is the equation at the top once you finish the division. So y equals 3x minus 3. And then we didn't ask you for this, but I'm going to talk about it for just a second. The factor that cancels out causes a hole at that x value, so at x equals 2. If you want to find that as an ordered pair, you need to evaluate f of 2, and you need to do it in the reduced form. So we'll do that in one of the next problems when we graph them. So this is just kind of a side note. That's what happens to that factor. Okay, now we're going to be getting into the ones where we're actually going to graph the rational function. So there's some things that you're going to know before, and we've got them listed here, before you actually start graphing. We want to know if we have any x-intercepts. We want to know if we have a y-intercept. We want to know if we have any vertical asymptotes or horizontal asymptotes or obliques possibly. We want to also know if we have any holes. Okay, so we're going to break it down and talk through how do you figure out each of these pieces. So if we're looking for x-intercepts, first of all, anytime you're graphing these rational functions, it's highly recommended that you factor everything first. So if I factor the bottoms here, this would be an x plus 2 and an x minus 2. And nothing is going to cancel since those are monomial on top and a binomials on bottom. So x-intercepts come from factors on top that have an x in them that don't cancel out. So since there's no x in the top at all, there are going to be no places where this will equal 0 because the top is always 4. So that means there are no x-intercepts. So this is not going to cross the x-axis. Y-intercepts are found by plugging in 0 for all of your x's. So f of 0 is 4 over 0 squared minus 4. That's 4 over negative 4 or negative 1. So that would be the ordered pair 0, negative 1. Remember, vertical asymptotes from the previous problems are found where you would have a factor still in the denominator that doesn't cancel out. So this first one, if you solve it, you'll get x equals negative 2. And if you solve the second one, you're going to get x equals positive 2, setting them both equal to 0. Let's talk about whether or not this one has a horizontal or an oblique. The original polynomial or rational function had no x's on top, so that's a degree of 0. And a degree of 2 in the bottom. So the top degree is smaller than the bottom degree. So that means this does not divide. So that is y equals 0. It's a horizontal asymptote. And then that would be none for the oblique. And there's nothing that canceled out. You only get holes if a factor cancels out. So we have all of our information here. And now we're going to go and put this on a grid so that we can graph. What's going to be happening here is we're going to be laying out a lot of boundaries and dashed lines to represent our asymptotes, and then we're going to try to figure out how many extra points do we need to plot, because it's not going to be enough information with what we have to get a good idea of what the graph should look like, because it does say we want to sketch the graph. So I'm going to go ahead and mark off a few tick marks here. Trying to keep them evenly spaced. Okay, and I'm going to put my vertical asymptotes in red. So I have one at negative 2. And at positive 2. And I label those x equals negative 2, x equals positive 2. I'm going to use, since I have a horizontal asymptote, I'm going to use blue to mark that. And y equals 0 is the x-axis because it has a y value of 0. So this is y equals 0. I'm going to use, let's just use black for my point. So at 0, negative 1, that's the only point I have on the graph. So this is definitely not enough points to figure out what's going on in the picture. So my recommendation, and I usually just make an XY chart to figure this out, every instructor has their own way, is I mark off anywhere that I have a vertical asymptote or an x-intercept, because I want points in between vertical asymptotes and x-intercepts as things I should plug in to see where the y value is. So we have a vertical asymptote at negative 2, so I always make a little mark about that. And I have one at positive 2. So I want to pick at least 2 x values on each side. That's just my rule of thumb. So I'm going to pick negative 3 and negative 4. Those are less than negative 2. I already have 0, so I'm going to pick negative 1 and 1 for between. And then bigger than 2, I'm going to pick 3 and 4. So you just want to take your calculator, or you want to write this out. I don't have a lot of room for scratch work, so I'm going to do it on the calculator. And you want to plug this into the most reduced form of your function. Just goes quicker that way. But for us, I'm just going to go back to the 4 over x squared minus 4. So if you square, and I may not need the calculator too much, but if you square negative 4, that'd be 16, minus 4 would be 12. 4 divided by 12. So I'm going to write this out actually. So f of negative 4 is 4 over negative 4 squared minus 4. So that's 4 over 16 minus 4, which is 4 over 12, or 1/3. So that's the y value for negative 4. That will also be the y value for positive 4 because the only thing we're doing with our x is squaring it, which means positive and negative 4 both give you a 16. That will not always happen, but it does here because the only thing we're doing is squaring x. Let's do negative 3. And again, you can use your calculator to check a lot of these, but show your work. So that would be 4 over 9 minus 5, or 9 minus 4, so that's going to be 4 over 5. So 4/5, which means positive 3 will also give me the same thing because it's 3 squared instead of negative 3 squared. And then negative 1 is 4 over negative 1 squared minus 4. That's 4 over 1 minus 4, which is 4 over negative 3. So negative 4/3. And again, 1 squared would also be a 1 minus 4. So that's going to also be negative 4/3. So this should be enough to graph a rough sketch of where this is happening. And the reason we're finding extra points is because the horizontal and vertical asymptotes are kind of like boundaries. You can never cross the red ones, the vertical asymptotes. You can possibly cross the horizontal, and there's a test for that, but we don't usually give you one on the exam that needs to worry about that. So hopefully your teacher showed you that test, but we're going to just focus on what we need to for this problem right now. So negative 4 is at 1/3, which is just a little bit above the x-axis. And, oh, sorry, that's not negative 4. Back up just one second. I'm at negative 3. Put that tick mark back. So at negative 4, we're at just above the x-axis at 1/3. At negative 3, we're at 4/5. So notice both of these points are above the blue line. So they're heading from this is not actually crossing here. This is just heading up towards that vertical asymptote. So headed towards positive infinity. In between negative 2 and 2, we have negative 1 down negative 4/3, which is negative 1 and 1/3. And we also have positive 1 down negative 4/3. So notice this graph is headed towards the vertical asymptote that's going to negative infinity, and this one is also going to negative infinity. And then when we plot this one, we'll see that there's some symmetry here. This is also 4/5 and 1/3. So our graph goes, it's above the x-axis in this first region, it's below the x-axis in the middle region, and above the x-axis in the last region. Okay, so let's look at one that has a little bit more going on with the pieces that we have to find. So we're looking at x squared minus 3x minus 10 over x squared minus 25. First step here is going to be to factor everything so that I can get the most reduced form. So this would be x minus 5, x plus 2 on top, over x minus 5, x plus 5, because of the perfect squares. So the x minus 5s are going to cancel out, so this reduces down to x plus 2 over x plus 5. So we need to find our x-intercepts, the y-intercept, the vertical asymptote, horizontal asymptote or oblique, depending on which one exists, and holes. So for the x-intercepts, we do still have a factor on top that is got an x in it. So that's going to be a possible x-intercept. So x plus 2 equals 0 would give us negative 2. So this is the x-intercept of negative 2, comma 0. To find the y-intercept, so this was x-intercept, you have to plug in 0 for all the x's. And again, I would plug it in the shortest reduced form. So 0 plus 2 over 0 plus 5. So we're doing f of 0. So that's just 2/5. So 0, comma 2/5. We did have a factor still in the denominator, so that means we have a vertical asymptote at x equals negative 5. The degree on the top matches the degree on the bottom. So when that happens, you have a horizontal asymptote, and it's always the leading coefficients of those leading terms. So 1 over 1. So that would be y equals 1. And that's only if your degree on top, highest degree, matches your highest degree in the bottom, which means we have no obliques. In this one, we did have a hole. This is a hole right here because it canceled out. So if we set that equal to 0, it'll tell us the x value of the hole. So it's at 5, and then to find the y value, you plug it into the reduced form. So this would be 5 plus 2, so this is to find the y, over 5 plus 5, which is 7/10. So we're going to have to do a rough estimate of where we think that is on the graph. Okay, so we have all of our information, so now we want to graph this. Let's draw our grid. It's not so easy to do when you don't already have the grid lines, but we're going to do our best. Okay, I had an x-intercept, I believe, at -2. Going to double check that by scrolling up. Yep. So at -2, I have an x-intercept. I have vertical asymptote at -5, so 1, 2, 3, 4, 5. X equals -5. I have a horizontal asymptote at +1 for the y value. And no obliques. I have a hole at 5 and 7/10. Okay, so when you have a hole, you draw an open circle. So I need to put another mark. So 5, so 1, 2, 3, 4, 5. 7/10 is still below 1. So see how that hole is just right below that line. And then we have our y-intercept of 2/5, which is, so that's supposed to be a -2/5? I don't think so. So let's look right here. Oh, I know what happened. Sorry. It's very late. I graphed my x-intercept on the wrong spot. Okay, so let's go back here. I was about to say it didn't look like it was making sense on where things were being drawn. So -2 was the x-intercept. So that's over here. Sorry about that. And then 0, 2/5 is the y-intercept. So I have lots of information about what's happening on the right side of this x-intercept. So remember, when I make my table, I want to write what I know. So I know I have a vertical asymptote at -5, and I have an x-intercept at -2, and I want to pick some points on each side. So I'm going to pick -6 and -7. Between -5 and -2, I can do -4 and -3. And I already know that 0 is 2/5. So maybe I'll pick 1 and 2, just 2 other points that we can plug in. So we're going to use the reduced version, since it's quicker to plug into, of x plus 2 over x plus 5. So -7 plus 2 over -7 plus 5. That's -5 over -2, or 5/2, because it comes out positive. -6 plus 2 over -6 plus 5 is -4 over -1, which is just 4. -4 plus 2 over -4 plus 5 is -2 over 1, so that's just -2. -3 plus 2 over -3 plus 5 is -1 over 2, so that's going to be -1/2. Let's see, 1 plus 2 over 1 plus 5 is going to be 3 over 6, so that's going to be +1/2. And 2 plus 2 over 2 plus 5 is 4 over 7. Okay? So we're going to plot these points. So -7, so this was -5, so 6, 7. 5/2 is 2.5, so up 1, 2.5. And then -6 is up at +4. So notice on this side of the red line, the graph is hovering in the top part of this quadrant. So if you think of this as 2 different possible choices. And then -4 is at -2. -3 is at -1/2. So notice that is going down towards the red here. And then 1 is at 1/2. And 2 is at 4/7, which is a little bit more than a half. So this is headed towards that hole, and it will actually continue. So if you want to prove whether or not this is ever going to cross its horizontal asymptote, just so I can show you here that I know for sure that this doesn't cross its horizontal asymptote, you set your value of your horizontal asymptote equal to that reduced function, so x plus 2 over x plus 5. You cross multiply and you try to solve it for x. So that would be x plus 5 times 1, and then x plus 2 times 1. And when you go to solve it, all your x's cancel out, and 5 does not equal 2. So that means it does not cross its horizontal asymptote. If you got an x value for that and you actually were able to solve, it would cross at whatever that x value is. So let's look at the next two problems. These are the last ones. So this is the inverses of functions. Now the way I solve this, I have a couple steps we're going to go through when we're trying to find an inverse. You're going to think of this as y equals x minus 3 to the 5th minus 2. And we're going to want to resolve this for x, essentially, because inverse functions just swap their domain and ranges. So we're going to add over 2. And then we're going to get rid of this 5th power. So we're going to take a 5th root. And then to get x by itself, we're going to add over 3. Now we've taken this function that was solved for y and we've solved it for x. This is called the inverse, but it's in the wrong format. We usually like f of x and x instead of x and y. So the way we rewrite this is that x becomes the inverse of the function and y becomes the x of your new function. So it's 5th root of x plus 2 plus 3. So that's my inverse function. Okay? And by swapping x and y again here, because now this is a y and this is an x, that's changing the domain and range. Because all we did in this first step is we resolved for a different letter. Now we've swapped domain and range. Okay, so let's do the same technique for number 24. We have, this is y equals 5x plus 4 over 3x minus 7. Now the problem here is you're trying to solve for x and you have 2 of them. So the best way to do this is to cross multiply first, just to get rid of the denominator. So this would be 3xy minus 7y equals 5x plus 4 times 1. And then here's the technique I always tell my students. You want to get all of the terms that have x on the same side if you're trying to isolate x. So I'm going to move over that 5x by subtracting. And I'm going to move this negative 7y over by adding because it does not have an x. Okay, so we're switching these two terms by adding and subtracting. Now that all your x's are on the same side, you can factor them out. And that takes it from having 2 x's down to having just 1. Final step here is to divide that parentheses to the other side. So x equals 7y plus 4 over 3y minus 5. Now, again, that was not, we haven't done any swap with our domain and range yet. This is just us resolving this equation for a different variable. So our rule is that x is going to become the y of this inverse, so f inverse of x, and these y's are going to become x's. So 7x plus 4 over 3x minus 5. Now, that's my inverse function. This also asked us to find the domain and range of h of x and h inverse of x. So I like to make a little chart. So I have h of x and h inverse of x. Sorry, this was supposed to be h, not f. And we're looking at what is the domain of each of them and what is the range. Since they're inverses, if you find the domain of both, you also know the ranges because domain and range just get swapped. So for this first one, you want to make sure that this bottom does not equal 0. So we would add 7, divide by 3. So you're just finding the domain of a rational function. So x cannot equal 7/3 in the original function. In the inverse, we'd say 3x minus 5 cannot equal 0. So we'd add 5 and we divide by 3. So this one says x cannot equal 5/3. Your ranges are both y values, not x values, and you just swap which one is which. So this one is the 5/3 and this is 7/3. And that's it. That's the end of this review. Hopefully this was helpful for you guys, and I hope you have a good time studying for your exam.